Hi, welcome to SB Chem classes. Today we are going to discuss an important topic in states of matter, that is real gas. First we are discussing about the behavior of real gas. We know ideal gas are imaginary gas, ideal gas are theoretical gas. But what about real gas? Real gas show two differences. Real gas show two deviation from ideal gas. What are the behavior of or deviation of real gas? Number one, volume of gas molecule is negligible when compared with the total volume of gas. Volume of gas molecule is negligible when compared with the total volume of gas. This is behavior of ideal gas. But real gas show deviation from this postulate. What about real gas? Volume of gas molecule is not negligible for real gas. So I am mentioning here not negligible for real gas. Another property of ideal gas is intermolecular force of attraction. Intermolecular force of attraction is zero at normal condition. Intermolecular force of attraction is zero at normal condition, because that means there is no such attraction. It is for ideal gas. Then what about real gas? Intermolecular force of attraction is not zero. Not zero for real gas. These are the main difference between real gas and ideal gas. Okay, real gas have a deviation from these two postulates, but we can convert real gas property to ideal gas behavior. For that, there are two conditions. Conditions for ideal gas. A real gas can be converted to the property of ideal gas at two conditions. Number one, at very high temperature. Number two, at very low pressure. You have to focus the point. At a very high temperature, at a very low pressure are the condition to be ideal gas, and both conditions are required, just not one property, not one condition, at a very high temperature and at a very low pressure. If you give both this property, a real gas can show behavior of ideal gas. Why? By this condition, real gas show nature of ideal gas. These are the two differences between real gas and ideal gas. When we give very high temperature, intermolecular force of attraction become zero. That means second deviation is cancelled at very high temperature. What will happen at very low pressure? Very low pressure means we have to increase the total volume. When we increase total volume, volume of gas molecule become negligible. So volume of gas molecule become negligible. That means first deviation is also cancelled. So these are the introduction points we have to know about real gas. Then we have to discuss about van der Waals equation. We know ideal gas equation. What it is? PV equal to nRT. This is equation for ideal gas. But real gas show deviation from ideal behavior. So real gas have another equation. I am not going through the detailed derivation. The equation is P plus an square by b square into v minus nb equal to nRT. P plus an square by b square into v minus nb equal to nRT. This is the equation for real gas. In this equation, there are two new terms, that is small letter a and b. These are known as van der Waals constants. A and B are van der Waals constants. This equation is known as van der Waals equation. Here you have to point out what is P. P is pressure of real gas. P is pressure of real gas. What is N? Number of moles of gas. What is V? V is volume of the vessel. Volume of the vessel. Then B I said N. T is absolute temperature. So this is equation for ideal gas. This is equation for real gas. And there are new terms A and B. A and B are known as van der Waals constants. Unit of A and B. We have to focus the point. Unit of A and B. We can simply calculate, determine unit of A and B like this. There is P for ideal gas. In that position, we have new term P plus an square by b square. So, I am using that. This P as P ideal equal to this P as P real plus an square by b square. We can simply arrange the equation and we will get A like this. What will be A? P ideal minus P real into v square by n square. If pressure is measured in atm, here atm, volume in liter, so it will become liter square. N in number of mole raised to minus 2. This is the unit of A. To find the unit of B, there is V term in this equation. Instead here V minus NB. So I am giving V ideal equal to V real minus NB. Actually this volume not indicate ideal real. I have to just distinguish between these two volume, giving V ideal and V real. What will be V here? V real minus V ideal by N. If volume is calculated in liter, it will be liter per mole. So we have two new terms A and B, and this A and B have unit. A unit atm liter square mole raised to minus 2. B have unit liter mole raised to minus 1. And another point is value of A and B. A and B are constants, but these constants depends on nature of gas. A and B are constants, and these constants depend on nature of gas. That means for oxygen gas there will be a particular A and B. For nitrogen gas there will be another A and B. So A and B depends on nature of gas. Within that we have to focus. Value of A depends on intermolecular force of attraction. We know value of A and B depends on nature of gas. What is the nature depends on A? That is intermolecular force of attraction. Similarly, B depends on volume of gas molecule occupied. B depends on volume of gas molecule occupied. These are the main points about the van der Waals equation. Okay. Next we have to know about the compressibility factor. Compressibility factor is used to determine deviation of real gas from ideal behavior. We know real gas show deviation from ideal behavior. We have to determine extent of deviation of real gas from ideal behavior. For that, there is simple equation. Compressibility factor Z is equal to PV by nRT. This PV by nRT can also be written as V real by V ideal. Volume of real gas by volume of ideal gas. That means this is experimental volume. This is theoretical volume. So experimental volume by theoretical volume, or volume of real gas or volume of ideal gas, or PV by nRT. Those are the equations for compressibility factor. If we have ideal gas, for ideal gas we know PV equal to nRT. If PV equal to nRT, then Z equal to 1. In case of real gas, what about real gas? For real gas, PV not equal to nRT. We know equation of real gas, that is P plus n square by V square into V minus NB equal to nRT. PV not equal to nRT. So Z not equal to 1. So based on Z value, we can determine deviation of real gas from ideal behavior. Based on Z value, real gases are two types. What will be two types? Z greater than 1 means Z can be, Z not equal to 1 means Z can be greater than 1, Z can be less than 1. So there are two types, Z greater than 1 and Z less than 1. If Z greater than 1, gas show positive deviation. If Z less than 1, gas show negative deviation. So there are two types of real gas, gas showing positive deviation, gas showing negative deviation. To be Z greater than 1, V real, volume of real gas, should be greater than volume of ideal gas. That means experimental value will be greater than what we expected or greater than theoretical value. To be Z less than 1, this V real should be less than V ideal. If volume of real gas is greater than volume of ideal gas, that means experimental volume is greater than theoretical volume. That means gas is less compressible than ideal gas. Gas is less compressible than ideal gas. By what we expected volume, the experimental volume is higher, so gas cannot be compressible, less compressible than ideal. If volume of real gas is less than volume of ideal gas, we can say that gas will be more compressible than ideal gas. That means if we expected particular volume, real gas compressed to less volume, so gases are more compressible. If a gas is less compressible, that indicate repulsion dominate repulsion dominate for this gas. So, if intermolecular repulsion dominate, that gas is known as positive deviation. If a gas is more compressible, if it can compress very well, that means attraction dominate. Attraction dominate. These are the two type of real gas. Okay, let's discuss the compressibility factor at a different condition. This is very special topic based for entrance examination. We have to consider one condition at a very high, at a very low pressure, number one. Another one at a very high pressure, number two. And at a very high temperature. These are the three conditions we have to check: at very low pressure, at very high pressure, and at very high temperature. At very low pressure means, volume of gas is very high. If volume of gas is very high, volume of gas molecule occupied, that is the B factor. B factor will be negligible. B factor will be negligible. Why? At very low pressure, total volume of gas is very high. So, volume of each molecule become negligible. We know value of B depends on volume of gas molecule occupied. That will be negligible. What is our real gas equation? That is P plus AN square by V square into V minus NB equal to nRT. In this equation, when B is negligible, we can convert the equation as P plus AN square by V square into V equal to nRT, because this factor is negligible. Let's minimize this equation for 1 mole species. If n equal to 1, the equation will be P plus A by V square into V equal to RT. P plus A by V square into V equal to RT. By multiplying PV plus A by V square into V, that become A by V equal to RT. What is Z? Z is PV by RT, because n equal to 1. So, let's divide both sides by RT. What will be? This is PV by RT. First, PV equal to RT minus A by V. Dividing RT on both sides, this becomes Z RT by RT 1 minus A by RTV. Z equal to 1 minus A by RTV. Okay, at very low pressure, B is negligible. So, this is the equation for real gas. This is the equation for compressibility factor. What will happen at very high pressure? At very high pressure, volume of gas molecule is very low. If volume of gas molecule is very low, the repulsion dominate. Here, repulsion dominate. If repulsion dominate, value of A will be negligible. Value of A will be negligible. Why? A depends on intermolecular force of attraction. Here repulsion dominate, so A will be negligible. So what will be our van der Waals equation when this factor is negligible? P into V minus NB equal to nRT. P into V minus NB equal to nRT. For 1 mole species, what will be the equation? And by multiplying PV minus P B equal to RT and PV equal to RT plus PV. This is the equation for real gas at very high pressure. What is Z? Z is equal to PV by RT. So let's divide by RT. This side become Z. It's become 1 minus PV by RT. 1 plus PV by RT. So this is the equation for real gas at very high pressure. This is the equation for compressibility factor at very high pressure. Let's check one more condition, that is at very high temperature. If we use very high temperature, gas molecule repel each other. So in this condition also repulsion dominate. Repulsion dominate. If repulsion dominate, what will happen? A will be negligible. A will be negligible. So the same equations can used at very high temperature. So I explained at very low pressure, at very high pressure and at very high temperature. We know condition for ideal gas. What is condition for ideal gas? Number 1, at very high temperature, at very low pressure. At very high temperature, A is negligible. At very low pressure, we already explained, B is negligible. So if we give both condition, A and B become negligible. If both A and B are negligible, equation will be PV equal to nRT. That is equation for ideal gas. Z will be 1. That is condition for ideal gas. So a real gas can show the behavior of ideal gas when we give both condition at very high temperature and at very low pressure. In this section, we have to focus about two gases that are hydrogen and helium gas. Hydrogen and helium gas dominate repulsion. Generally. For hydrogen and real gas, repulsion dominate generally. If repulsion dominate, we know A will be negligible. So, for hydrogen and real gas, we can use the equation at when A is negligible. When A is negligible, what are the equations? We already explained. That is PV equal to RT plus PV and Z equal to 1 plus PV by RT. These equations can be used for hydrogen and helium. Why? For these gases, generally repulsion dominate and A is negligible. These are the important points. These are the important points about the real gas behavior. Thank you.